I wanted to talk about how Crankshaft can be modeled for games or simulations. Let's first define what we want. We want a black box that converts torque input to the rotation of the crankshaft. More specifically, angle, angular velocity, and angular acceleration. That's our black box model. Now we will write the mathematical relation between input and output. Because our system is rotating, it has inertia, and we know that inertia and torque have a linear relationship with respect to second derivative of angle. Secondly, we sense that when we release the rotating crankshaft, it will stop. That is because of the damping, and we will denote it by the letter C. Damping and torque have a linear relationship with respect to angular velocity. Lastly, the K, which is coefficient of the spring constant. Spring constant and torque are connected with the Hooke law, that is, with the crankshaft angle. And all the sum is equal to the torque on the crankshaft. But we know that when we rotate the crankshaft and release it, it won't turn back its starting angle. Therefore, we will neglect the spring coefficient. And here, we have a mathematical equation that represents the specific input and output relation that we want. But because we will use that model in discrete time, and because the equation is differential equation, we can't escape that easily. We have to convert that relation to such a form that it will be able to calculate it in computer loop. To do that, first we will select a frequency. While choosing a frequency, it's good to think about the extreme cases. Our model will not run above 20,000 RPM. In other words, over 333 revolutions per second. Yet there is one more important section to think about is the inside of the cylinders. We know that every time the crankshaft rotates once, the pistons moves in the cylinder twice. So if we multiply 333 by 2, we can now be able to sample the pistons one stroke. But the thing is, with that frequency, at 20,000 RPM, while the piston is moving like that, we will see a piston like that. To make it smoother and more accurate, we want to sample at least 10 times, like that. That's why we multiply with 2 and 10. So we can simply see that we need at least 6666 Hz to run a proper model at 20,000 RPM. To make it even more reliable, we select the frequency as 10,000 Hz, or sample time is 0.0001 second. Alright, after this point, we have a bunch of methods to solve that equation. I'm going to show you how to solve with two of my favorites. The first one is using discrete transform function. We will start with Laplace transform. In our case, the crankshaft will start rotating from a stationary condition, so this difference will be 0. Then we rearrange the equation to get theta s divided by Ts. Perfect. Now we have our continuous time transfer function. Before the next step, we have to calculate the inertia and damping for the 4-cylinder engine. If we model a crankshaft in 3D engineer program like Autodesk Fusion 360, after the apply material, it can calculate the inertia for us and it's 0.04. Now I will make a shortcut here and roughly calculate the inertia effects of the engine components on the crankshaft. In system dynamics it's valid, so I will make it as simple as possible and I will make better estimation after a while. From the one flywheel data I found on the internet, the inertia of the flywheel can be calculated like that. Because it's a 4-cylinder engine, I multiply the effect of pistons and rods by 4, and I'm estimating pistons as a point rotating around the center of the crankshaft. Lastly, adding the inertia of the connecting rod around the rod's small end is calculated by Fusion 360, and I'm multiplying by 1.5 to round up all the parts I didn't include and my possible miscalculations. On the damping side, there is this equation to calculate the viscous torque on the journal bearing at certain RPM. We can rearrange it to find damping ratio, and if we do the math, it's 0.0017. In general, there are 5 journals between the crankshaft and block, 4 for the rods and crankshaft, and 9 in total. For the pistons, I found out that on some papers, people calculated the damping between piston and cylinder wall at about 0.05, multiplying the result with the correction factor, and here we have very roughly but reasonably estimated parameters. We can finally move on to discrete time. One and easy method for that is using Matlab C to D command. Here the result is stored in that parameter. First input of the function is our continuous time transfer function, and the second one is sample time. We run that code block to get the result, and Matlab will give us something like that. That's our transfer function in Z domain with 0 order holds. Now we take that function and multiply it with the second order hold to make it usable in real time. We cross multiply the result and I want to point out that terms. While converting the equation from z domain to time domain, z to the power 0 is the current time, z to the power of minus 1 is the previous sample, z to the power of minus 2 is the second before the current sample, and so on and so forth. To get the current angle, we send these terms to the other side of the equation. And here we have it, the discrete model of the crankshaft. Let's summarize what we do. We draw our black box model, derive the mathematical relationship between input and output, choose a proper frequency, use Laplace to get the continuous time transfer function, calculate the parameters, convert continuous time transfer function to discrete time, turn back to the time domain and rearrange the equation to get what we want. Okay, set this solution aside and move on to the second method, the state space model. In this model, we write our equation in particular matrix form and decrease our equation to first order differential equation. X dot represents the derivative of the state vector, A is the system matrix, X is the state vector, B is the input matrix, U is for input vector, Y is for output vector, C is the output matrix, X for state vector, D is feed-forward matrix, and U is again input vector. The state of the system can be represented as a vector, and every state element is one of our control variables. Now, I take that differential equation and add the spring coefficient again to make our calculations more parametric. At the end, I will set the k as 0 anyway. These states are at most first order derivative, which means it will not be a problem. However, we should convert that second order differential term to the first order. To do that, we can redefine the states. By the way, when there is a small number of states and equations, redefining the states looks unnecessary, I know, but it's good to know that there is a method like this. Let's say x1 is theta, x2 is derivative of x1, and it is also equivalent to the theta dot. Then the derivative of x2 will be equal to the derivative of x1, which means the second derivative of theta. Now our states are x1, x2, x1 dot, x2 dot, and all of them at most first order. Keep in mind that. In the first step of the state space representation, we keep the derivative of the states in the left-hand side. In our case, the derivative of the state is a vector of x1 dot and x2 dot. So according to our conversation table, x1 dot is equal to the x2. Although they are 0, we can show the other terms. To get the x2 dot, we have to write our differential equation with a new variables. The second derivative of theta is equal to the x2 dot. The derivative of theta is equal to x2, and lastly, theta is equal to x1. Rearrange the equation to keep x2 alone in the left-hand side. And here we have our second element. Convert these two equations to the matrix form. Finally, replace the temporary variables with the original variables. The good thing about the state space is that the written matrix form can update the states itself recursively. The only thing we should do is sample the states that we want to. And we can do it simply like that. So we can write all the A, B, C, and D matrices like that. To sum up, we draw our black box model, derive the mathematical relationship between input and output, convert our differential equation to the state space form, choose a proper frequency, and calculate the parameters. I made a Matlab simulating example to compare all the models that we were talking about. At the very top, we have our continuous time transfer function. Below that, discrete time transfer function with zero order hold. The function is the same as the one we calculate, but you notice that the precision of the constants are extremely high. That is important because when the precision is low, more the frequency is high, more the computing errors will accumulate, and the system will not work properly. To get the precise values, we run the Matlab script. Then print the numerator and denominator values of the discrete transfer function with the sprintf function, which will give you the specific amount of digits. Okay, these two are straight Matlab block for reference. This Matlab function is discrete time transfer function with second order holds. We can see that the inputs is torque and output is angle. E1 is for the previous angle sample, E2 for the second before the current sample, same for the torque. The corresponding values are feedback from the output with the 1 or second order delay. And the equation is the same as we calculate. Last one is state space model. We can see that all the parameters and matrices are defined at first. And then our general form is written. Again, torque is input and the y, which is angle, is output. X is feedback which integral of the x dot and the initial conditions are 0. Before running the file, we have to set the step size from the model settings. We change the variable step to the fixed step and the step size, which is the sample time, is equal to 0.0001. That way our model will work properly. After solving the system with the 2-second step input, we can see at the output scope all the models are behave exactly the same. The crankshaft rotates 62 radians and stops within 5 seconds. We are sure that the models are correct. Let's integrate the same model into C# now. Starting with the discrete transfer function, we define the constant variables, input and output arrays, and the other outputs that we will derive from the model output. In the loop, we write the equation directly. Angle 0 is the angle at the current time, the angle 1 is previous, and so on and so forth. We can calculate the angular velocity by dividing the change in the angle within one step by the sample time. And we know that the angular acceleration is equal to current time torque divided by the inertia. Lastly, we update the values of the variables and the loop continues. For the state space example, we define system parameters, all the matrices and the vectors that we talk about. In the loop, we start defining the system matrix, then the input vector, output vector, and feed-forward vector, following with calculating the x dot and integrating the x dot to find out x. Then all we need to do is extract all the data we want and assign them. That's it. I already implemented the equations to the Unity. You can find out all the code and project files in my GitHub account. To run the models, I prepared a 10,000 Hz timer and created the same input that we used on Matlab model. Only by calling the dynamic model functions, we are done. To make it visually visible, I add 2 crankshaft models, and the left one is for the state space model, the right one is for the discrete transfer function. In the update, I update each rotation. If we run the simulation, we can see both models is working, and they are reaching the 62 radians and stops within 5 seconds as well, almost exactly the same as each other and the Matlab model. We can look at the pros and cons of the models to determine which model to use. Preferably, I use the discrete transfer function for time-invariant dynamical systems and state space for time-varying models. In the next chapter, we will dig into the kinematics and dynamics of the slider crank mechanism, and also add rods and pistons to the Unity. Stay tuned!